Hello there, and welcome to Sleepy Science Stories. Tonight we are going somewhere that is not there. We are going to a place in the universe where almost nothing exists. Not a dark planet, not a cold moon, not even the thin wisps of gas that drift between the stars. We are going to a place where the universe simply forgot to put anything. A hole in the fabric of everything, 330 million light years across. It has a name. Astronomers call it the Boötes Void. The name comes from the constellation Boötes, the herdsman, in whose direction this emptiness lies. But scientists who discovered it had another name for it first. They called it the Great Nothing. And that name, perhaps, is more honest. To understand why this place is strange, you need to hold one number in your mind: 330 million light years. That is the diameter of this void. A single light year is already almost incomprehensible. Light travels at 300,000 kilometers every second. In 1 year, it covers nearly 10 trillion kilometers, and the Boötes Void is 330 million of those years wide. If you tried to cross it at the speed of light, you would need 330 million years. When you started, there were no humans on Earth. There were no mammals. There were barely fish. You would cross the entire span of complex animal life on this planet and still not reach the other side. In a region that size, there should be roughly 2,000 galaxies, each galaxy containing hundreds of billions of stars. Instead, astronomers have found 60, just 60, clustered in a narrow tube through the middle, like a handful of dust in an empty cathedral. Tonight, we are going to understand what that means. We will talk about how the universe is structured and why emptiness is part of that structure. We will talk about how this void was discovered, almost by accident, by a team of astronomers who were building a map of the sky. We will talk about what the void is made of, which is not nothing, but close enough to nothing, that the difference barely matters. And we will sit with the thought that has followed this place since its discovery. If our galaxy, the Milky Way, had formed inside the Boötes Void, we would have looked out into the universe for our entire history and seen almost nothing. No neighboring galaxies, no galactic clusters, no cosmic web of light. We would have believed, with total certainty, that we were alone, that our galaxy was the only island of stars in an otherwise empty universe. We would have been completely, profoundly wrong. That thought is worth sitting with. The idea that what we can see shapes what we believe, and that the universe contains places where the visible and the true are so far apart that the gap between them could swallow a civilization. If you enjoy these sleepy science journeys, please consider liking or subscribing. It helps other curious minds find their way here. But for now, let your body settle. Let the sounds of the day become quieter. And let your mind drift outward, past the stars, past the galaxies, into a region of space so empty that the silence has a different quality there. Deeper, older, more complete. The great nothing is waiting. Let us go. There is one thing worth understanding before we begin in earnest. The universe we are about to explore is not the universe of everyday intuition. It is not the universe of the night sky, where the stars seem scattered freely, but close enough to count. It is the universe of the very large. The universe of structures so massive that entire galaxies are the smallest relevant units of measurement. At this scale, things that seem familiar become unrecognizable. A galaxy containing hundreds of billions of stars, each one a sun, counts as a single data point in a map. The distance between neighboring galaxies is measured in millions of light years. The structures those galaxies form, the clusters and superclusters and filaments, stretch across hundreds of millions of light years. They are themselves just the threads of a web, whose full extent spans the entire observable universe. This is the scale at which the Boötes Void exists, not the scale of planets or stars or even galaxies in isolation. the scale of the largest structures in the known universe. And at that scale, the void is not just large. It is one of the defining features of the universe's architecture. To move through the scale from where you are now to the Boötes Void, try this. Start with your own body. Expand your awareness to your room, then your neighborhood, then your city, then your country, then the planet, then the solar system, 80 light minutes across, then the distance to the nearest star, 4 light years, then the galaxy, 100,000 light years wide, then the local group, a few million light years, then the supercluster, 500 million light years, and somewhere within that supercluster, the Boötes Void, 330 million light years of almost nothing, waiting quietly at the edge of what we can see. Each step in that sequence is a multiplication by a factor of millions. The void is not just far. It is a different order of existence, something that exists at a scale where the word far has stopped being useful. That is where we are going tonight. Into the genuinely incomprehensible, and the only way to go there is slowly, with your eyes closed, and all the time in the world. Take a breath, let it go, and let the numbers dissolve into feeling. 330 million light years. Not a measurement now, a texture, a quality of the dark behind your eyes, something vast and patient and real, waiting at the edge of the observable universe, exactly where it has always been. Before we can understand the Boötes Void, we need to understand the shape of the universe. From where we stand, the universe looks like a scatter of stars. On a clear night, far from city lights, you can see several thousand of them. They seem spread across the sky in no particular pattern. Random, evenly distributed. The universe, from our vantage point, looks like a jar of spilled salt. But that appearance is an illusion of scale. It is like looking at a forest from inside a single tree. You see bark and branches and nearby leaves. You cannot see the shape of the forest, the clearings, the dense groves, the rivers that cut through it. To see the shape of the forest, you need to be above it. When astronomers began measuring the distances to galaxies in the 1970s and 1980s, they were climbing above the forest. For the first time, they could place galaxies not just in 2 dimensions on the sky, but in 3 dimensions in space. And the shape that emerged, as those maps filled in, was nothing like a jar of spilled salt. The universe, on the largest scales, looks like a sponge, or like foam in a bathtub, or like the web a spider builds, if that web were 3-dimensional and stretched across billions of light years. Galaxies do not scatter randomly through space. They gather along thin sheets and long filaments, enormous threads of matter, that connect clusters and superclusters of galaxies. These filaments form the bright strands of the cosmic web. And between the filaments, there is almost nothing. The spaces between the filaments are called voids. They are roughly spherical regions, where the density of matter is far below the average. The galaxies that would otherwise fill these spaces have been gravitationally pulled away, drawn toward the nearby filaments and clusters. The voids have been emptied out, slowly, over billions of years, as matter migrated toward the bright dense places, and left the spaces between them barren. This process began almost at the beginning of the universe. In the first moments after the Big Bang, matter was distributed nearly uniformly. But nearly is not exactly. There were tiny fluctuations, microscopic differences in density, that quantum mechanics had written into the fabric of the young universe. Some regions were, by an infinitesimal amount, denser than others. Over hundreds of millions of years, gravity amplified those tiny differences. The denser regions pulled in more matter. The less dense regions lost matter. The small fluctuations grew. The cosmic web began to take shape. What we see today, 13.8 billion years later, is the result of that amplification. The filaments are the regions that won the gravitational contest. The voids are the regions that lost. The voids are not accidents or anomalies. They are as fundamental to the structure of the universe as the filaments themselves. The cosmic web cannot have bright threads without dark spaces between them. Most voids are tens of millions of light years across. Some are larger. The Boötes Void is in a category almost by itself. At 330 million light years, it is one of the largest voids ever identified in the observable universe. It is not just a void, it is a supervoid. And even among supervoids, it is exceptional. There is something worth pausing on before we move forward. The universe is mostly empty, not mostly full of stars, with some empty spaces between them. Mostly empty, with some thin threads of matter where the galaxies live. If you could map every galaxy in the observable universe and remove all the space between them, the total volume of all galaxies combined would be a tiny fraction of the total volume of space. The voids are the dominant structure. The filaments are the exception. We tend to think of space as the backdrop and matter as the main event. But at the largest scales, the voids are the main event. They define the shape of everything. The galaxies are just the glowing edges of the emptiness. The Boötes Void is the largest, most dramatic example of that emptiness we have found. It is the universe, showing its dominant feature at its most extreme. Let your mind hold that image. The cosmic web, stretched across billions of light years, with its bright filaments and dense clusters. And in one region, larger than most, the web simply does not exist. Just space. Clean and cold and 330 million light years across. There is one more thing worth understanding about voids before we move forward. Voids are not static. They are growing. As the universe expands, the matter on the edges of voids continues to flow toward the surrounding filaments. The voids become slightly larger, slightly emptier, with each passing billion years. Dark energy accelerates this process. The faster the universe expands, the faster the matter that might otherwise fall back into the void is carried away. Voids are, in a sense, the expanding universe made visible. They are the spaces that dark energy carves out of the fabric of matter. Every void in the universe is a record of that carving. The Boötes Void is the deepest and widest carving we have found, a monument to the force that dominates the universe, made visible in the shape of absence. The cosmic web also evolves. It is not a fixed structure. The filaments are slowly becoming denser as more matter flows along them toward the clusters and superclusters at their intersections. The voids are slowly growing larger as the matter that bordered them drains away. Dark energy accelerates both processes. The universe is becoming more structured and more empty simultaneously, more concentrated in the filaments, more barren in the voids. In the very long run, dark energy will win. The expansion of the universe will eventually outpace the ability of gravity to hold even the filaments together. The web will dissolve. The voids will merge into a single, undifferentiated emptiness. But that is far in the future. For now, the cosmic web still holds its shape, and the Boötes Void still holds its emptiness, patient and vast, a permanent reminder of the force that shapes everything. The Boötes Void was not found by someone looking for it. It was found by someone making a map. In 1977, a group of astronomers at Harvard began a project called the CFA Redshift Survey. CFA stands for Center for Astrophysics. The goal was straightforward, at least in principle. They would measure the redshifts of thousands of galaxies and use those measurements to build a three-dimensional map of the universe in the region of sky around us. Redshift is the key tool for measuring cosmic distances. When a galaxy is moving away from us, the light it emits is stretched. The waves of light become longer. Longer waves of visible light appear redder. The faster the galaxy is moving away, the more its light is shifted toward the red end of the spectrum. And because the universe is expanding and farther galaxies are receding faster, the amount of redshift a galaxy shows tells you how far away it is. The survey was painstaking work. Each galaxy required telescope time. Each spectrum had to be measured. Each redshift had to be calculated. The team worked for years, accumulating data, building the map galaxy by galaxy. By 1981, the map had grown large enough to reveal something unexpected. Robert Kirshner, one of the astronomers on the survey, was analyzing data from 3 separate regions of the sky. All 3 pointed toward the constellation Boötes. And in all 3, there was a gap, a region of redshift space, which corresponds to a region of physical space, about 700 million light-years from Earth, where no galaxies appeared at all. In a random, uniform distribution of galaxies, the probability of a gap this large appearing by chance is vanishingly small. The team ran their analysis carefully. They checked their data. The gap was real. Kirshner and his colleagues published their results in 1981. The title of the paper was quiet and technical, as scientific papers tend to be. But what they were describing was extraordinary. A region of space, larger than anything previously found, almost completely devoid of galaxies. They named it, informally, the Great Nothing. The name stuck for a while, before the more technical term, Boötes Void, took over. But the informal name captures something the technical name does not: the psychological weight of what they had found. Not just an absence of data, an absence of universe. In the years following the initial discovery, other astronomers turned their telescopes toward the void. They wanted to know exactly how empty it was. The first surveys had found no galaxies at all. Later, more sensitive surveys began finding a few. By 1987, a team including Kirshner found 8 galaxies in the void. By 1988, 3 more were identified. By 1989, 15 more. By 1997, the total count had reached 60. 60 galaxies, in a region where 2,000 would be expected. And those 60 are not distributed evenly through the void. They are clustered in a narrow filamentary structure, a tube running through the middle of the void. The rest of the void, the vast majority of its volume, contains nothing that has yet been found. The shape of those 60 galaxies is itself a clue about how the void formed. A tube of galaxies running through the center of a void is exactly what you would expect if the void formed by the merger of many smaller voids. Imagine many soap bubbles, each one smaller than the Boötes Void, merging together into one large bubble. Where the original bubble walls met, there would be remnant filaments. The 60 galaxies in the Boötes Void may be the remnants of those ancient walls, the fossils of the smaller structures that merged into the supervoid we see today. This is the leading hypothesis for how the Boötes Void formed. Not a single dramatic event, but a slow coalescence of smaller emptiness over billions of years. The cosmic web evolved, and the voids gradually merged, the way bubbles and foam merge when you watch them closely enough. The Boötes Void is, in this sense, a very old structure. It has been accumulating its emptiness for most of the age of the universe. Let that settle. A hole in the universe, growing slowly larger since before the Earth existed. Now spanning a distance that would take 330 million years to cross, at the speed of light. Found by a team of astronomers building a map of the sky, and recognizing that their map, in one enormous region, was simply blank. The blank region on that map is one of the most significant discoveries in the history of astronomy. Not because it was the first void found. Small voids had been identified before. But because of its scale, because of what its existence implied about the structure of the universe, because of the question it asked, and still asks, about how something so large could have become so empty, and whether our standard models of cosmology are truly adequate to explain it. Kirshner and his team had not gone looking for the Great Nothing. They had been building a picture of the universe, galaxy by galaxy, measurement by measurement. And the picture, when it was large enough to show its own shape, contained a hole. A hole that the universe had put there, quietly, over billions of years, while no one was watching. The discovery of the Boötes Void is one of those moments in science when the data returns something unexpected, not predicted, and not fully explained for decades afterward. What Kirshner and his team found in 1981 was not just a large void. It was evidence that the universe was structured on scales that no one had fully anticipated. The surveys of the 1970s had revealed that galaxies clustered, that they were not scattered randomly, but the scale of the clustering and the scale of the corresponding voids was larger than most models had suggested. The Boötes Void was the first dramatic proof that the universe's structure extended to scales of hundreds of millions of light years. It changed the way cosmologists thought about the universe's architecture, and it opened a decades-long conversation about whether our theories of how the universe evolved were truly adequate to produce structures this extreme. The name Great Nothing is evocative, but it is not quite accurate. The Boötes Void is not nothing. It is not a hole in space, in the literal sense. Space still exists there. The laws of physics still apply. If you traveled through it, you would not notice anything different about the fabric of space-time. It is not a black hole. It is not a region where matter has been annihilated. It is simply a region where matter, and especially the matter that forms galaxies, is present at far lower than average density. What is inside the Boötes Void? The 60 known galaxies, scattered sparsely through its interior, each one a collection of billions of stars. Each one surrounded by the thin gas and dust that fill the space within galaxies. Each one separated from its nearest neighbor by a distance roughly 10 times greater than typical galaxy separations elsewhere in the universe. Beyond those 60 galaxies, the void contains dark matter. Not nothing, but far less than average. Cosmic voids have lower dark matter density than the filaments and clusters. The dark matter that was once more evenly distributed has been drawn toward the surrounding structure over billions of years. What remains in the void is the residue. The void also contains a very thin intergalactic medium, gas, mostly hydrogen and helium, at temperatures and densities so low that detecting it requires specialized observations. This gas is not dense enough to form stars or galaxies. It just drifts, extremely slowly, through the interior of the void, at densities far below anything that could be called a significant concentration of matter. There may also be intergalactic magnetic fields, though measurements of fields in voids are extremely difficult, and the data is sparse. What is not in the Boötes Void is the thing that makes it remarkable. There are no galaxy clusters, no superclusters, no bright filaments of densely packed galaxies, no regions where thousands of stars are being born every year in clouds of gas compressed by the gravity of nearby structure. The void is, by any reasonable measure, one of the emptiest places in the observable universe. To understand the scale of that emptiness, consider our nearest galactic neighbor. The Andromeda Galaxy sits about 2.5 million light-years from the Milky Way. That distance, vast as it seems to us, represents about 1% of the diameter of the Boötes Void. You could fit roughly 100 Milky Way to Andromeda distances across the void, and still not reach the other side. Consider the observable universe itself. The observable universe spans about 93 billion light-years across. The Boötes Void represents roughly 0.3% of that diameter. It sounds small, but three-dimensional volume does not scale linearly with diameter. The volume of the Boötes Void is an almost incomprehensible fraction of the total observable universe. There is a question that astronomers have debated since the void was first identified. Is the Boötes Void genuinely anomalous? Or is it simply a large but not extraordinary example of the voids that exist throughout the cosmic web? The answer depends on what models predict. The standard model of cosmology, called lambda CDM, successfully predicts many features of the large-scale structure. It predicts a cosmic web of filaments and voids. It predicts a distribution of void sizes. And for most observed voids, the predictions match the observations well. The Boötes Void is at the large end of the predicted distribution, but not dramatically beyond it. Current cosmological models can accommodate its existence without requiring any new physics. It is extreme, but not impossible. However, some astronomers have noted that the void is surprisingly empty, even for its size. The 60 galaxies found within it represent a deficit more dramatic than the size alone would suggest. Whether this deficit requires explanation beyond the standard model is a question that has not been fully resolved. It may be the result of random variation in an inherently probabilistic universe. Let your mind wander through it for a moment. The void. The 60 lonely galaxies, each one an island of light in a sea of darkness far larger than any sea we have words for. The vast distances between them, the silence. And then consider this. The light from those 60 galaxies has been traveling for 700 million years to reach our telescopes. What we see when we look at the void is not what the void looks like now. It is what the void looked like when the first complex animals were appearing on Earth, when the Cambrian explosion had just begun. The universe does not give us a live picture. It gives us a delayed one, stretched across time in proportion to distance. The void we study tonight is the void as it was, hundreds of millions of years before the first fish swam in any ocean. Whatever the void looks like right now, in this present moment, is information that has not yet had time to reach us. We are always looking into the past. The further we look, the deeper into time we see. And the Boötes Void, at 700 million light years away, is deep time indeed. Every time we look at the void, we are looking at the past. The 60 galaxies we have cataloged were 60 galaxies as they existed, hundreds of millions of years ago. Some of those galaxies may have changed dramatically since then. They may have merged with each other. They may have consumed nearby dwarf galaxies. Their star formation rates may have risen or fallen. We are looking at a snapshot, frozen in the light that left the void before the Cambrian explosion on Earth. Whatever the void contains right now, tonight, we will not know for a very long time. The information is on its way, but it will not arrive for hundreds of millions of years. We are patient watchers of a universe that is always showing us its past. Always, without a single exception. There is a sentence about the Boötes Void that has followed this place since its discovery. It was spoken by the astronomer Greg Aldering, one of the scientists who spent years mapping the interior of the void. And it goes like this. If the Milky Way had been in the center of the Boötes Void, we would not have known there were other galaxies until the 1960s. Sit with that for a moment. We discovered other galaxies in the 1920s. Before that, astronomers debated what the fuzzy patches of light visible in powerful telescopes actually were. Some argued they were clouds of gas within our own galaxy. Others argued they were distant islands of stars, entire galaxies like our own, too far away to resolve. Edwin Hubble settled the debate in 1924 by measuring the distance to the Andromeda Galaxy and showing it was far outside the bounds of the Milky Way. That discovery transformed our understanding of the universe. Before it, we thought the Milky Way was the universe. After it, we understood that the universe contained billions of galaxies, each one vast, each one ancient, each one full of stars. Now imagine that discovery had never been possible. If the Milky Way had formed inside the Boötes Void, the nearest large galaxy would have been hundreds of millions of light years away. Our telescopes, even modern ones, would have seen almost nothing beyond our own stars. The fuzzy patches that gave Hubble his data simply would not have been there to see. The nearest galaxies would have been invisible, too far, and too faint for any instrument we have built. Astronomers would have looked out into the universe, with every tool available to them, and seen only our own galaxy. They would have concluded, reasonably and incorrectly, that the Milky Way was alone, that the universe was one galaxy, surrounded by empty space, extending to infinity. Every cosmological model would have been built around that assumption. Every theory of the universe's origin, its structure, its fate, would have begun from the premise that we are the only island of stars in the darkness. We would have been wrong. Completely, profoundly, cosmically wrong. And we would have had no way to know it. This thought experiment is not just intellectually interesting. It is a specific, concrete example of a general principle that should make us careful. Our understanding of the universe is limited by what we can observe. What we can observe is limited by where we happen to be. And where we happen to be is a matter of chance. We are not in the Boötes Void. We are in a relatively ordinary region of the cosmic web, surrounded by a modest supercluster, within range of thousands of observable galaxies. That location has given us a view of the universe rich enough to reveal its large-scale structure. We can see the filaments. We can map the voids. We can identify the cosmic web. We understand, at least in outline, the shape of everything. But the astronomers of the Boötes Void, if there were any, would not have that view. They would be doing cosmology with one hand tied behind their back, without knowing the hand was tied. How many other things do we not know, because of where we happen to be? How many structures, how many patterns, how many fundamental truths about the universe are invisible to us? Not because they do not exist, but because our location in space and time has placed them beyond our reach. The Boötes Void does not answer that question, but it makes the question unavoidable. And there is one more layer to this thought experiment, worth turning over slowly. The galaxies of the Boötes Void are not empty. They presumably contain stars. Many of those stars presumably have planets. Some of those planets may be habitable. Life may have arisen there. Civilizations may have developed. And those civilizations, looking out at their universe, would have seen a sky of almost perfect darkness beyond their own galaxy. They would have had no Andromeda to point a telescope at, no Virgo cluster to map, no cosmic web to discover. Their cosmology would have grown from observations of one galaxy surrounded by void. Their deepest questions about the nature of the universe would have been asked against a backdrop of extraordinary loneliness. Whether any such civilization exists, we cannot know. But the possibility is real. And it is a reminder that the question, what is out there, does not have a universal answer. It has a local one. It depends on where you are standing when you ask it. There is something quietly humbling about that. We have built our entire picture of the cosmos on the view from this particular location, a view rich enough to reveal filaments, voids, the cosmic web, the Big Bang's afterglow. But a different location would have given a different view, a different cosmology, different questions, different certainties. We did not choose where to be born. We inherited this view, and we have made the best of it. The astronomers of the void, if they exist, inherited their view too. And the universe looks entirely different. From inside the great nothing. That is not an abstract observation. It is a specific, concrete statement about the epistemology of any civilization that might exist in the void. Their science would have developed differently. Their philosophy of nature would have developed differently. Their sense of place in the universe would be fundamentally different from ours. They would be, in a deep sense, alone in a way that we are not. Not just practically alone, in that no one has visited, but cosmologically alone, surrounded by emptiness on a scale that would make the very concept of other worlds, other civilizations, other galaxies, feel like pure abstraction. The universe, from inside the void, would seem to confirm the worst loneliness. An island in an infinite sea, No neighbors. No cosmic web. No context. Just the galaxy and the darkness. The Boötes Void is not just a curiosity. It is a laboratory. Cosmic voids are among the most powerful tools astronomers have for studying the forces that shape the universe at the largest scales. And the most important of those forces is one we barely understand. Dark energy. Dark energy is the name we give to whatever is causing the universe to expand at an accelerating rate. In 1998, two independent teams of astronomers studying distant supernovae discovered that the expansion of the universe is speeding up. Galaxies are not just moving apart. They are moving apart faster and faster as time goes on. Something is pushing them. Something is adding energy to the fabric of space itself, causing it to expand with increasing speed. We do not know what that something is. We call it dark energy because it is invisible and because it carries energy. Energy is the most neutral word we have for something whose nature remains entirely unknown. Dark energy makes up roughly 68% of the total energy content of the universe. It is the dominant component of everything, and we have no idea what it is. Cosmic voids are sensitive to dark energy in a way that other structures are not. Inside a void, the density of matter is very low. Gravity, which is generated by matter, is correspondingly weak. Dark energy, which acts uniformly throughout space, is therefore more dominant inside a void than it is in a dense filament or cluster. The expansion of the universe, driven by dark energy, is less opposed inside the void than outside it. Voids therefore expand faster than the universe as a whole. By measuring how voids grow over time and comparing those measurements to the predictions of cosmological models, astronomers can test theories of dark energy. If the theory is right, the void should grow at a specific rate. If the rate differs, the theory needs revision. The Boötes Void, as one of the largest known voids, is a particularly powerful probe of this kind. Its size means that the effects of dark energy are larger and easier to measure there. Its emptiness means that the competing effects of matter are smaller and easier to subtract from the data. Missions like the Euclid Space Telescope, launched by the European Space Agency, are specifically designed to study the large-scale structure of the universe, including voids. Their goal is to constrain the properties of dark energy by measuring millions of galaxies and mapping the void distribution across billions of light years. These surveys will build a statistical picture precise enough to test the most subtle predictions of dark energy models. The Boötes Void will be part of that picture, not as a special case, but as an extreme data point, one end of the distribution of void sizes, where the signal is strongest and the measurements most informative. There is also the question of neutrinos. Neutrinos are among the most abundant particles in the universe. They are nearly massless, electrically neutral, and interact with almost nothing. They stream through ordinary matter without slowing down, and because of their tiny mass, they do not cluster the way other matter does. They flow in and out of voids freely. The distribution of neutrino mass, which is still poorly measured, affects the statistical properties of cosmic voids in subtle but detectable ways. Voids that are slightly too small, or slightly the wrong shape, compared to the predictions of models, can be signatures of neutrino mass. By studying enough voids, precisely enough, future surveys hope to measure the combined mass of all neutrino species, a measurement that has been beyond the reach of particle physics experiments alone. The universe is using its own structure, the pattern of emptiness and filament, to encode information about its most elusive particles. The Boötes Void is one of the pages of that encoded message. What makes this beautiful and worth sitting with slowly is the connection between the very large and the very small. The biggest empty structure in the observable universe, carrying information about particles so tiny that they pass through the entire Earth without noticing it is there. the cosmic web, and the quantum world, connected by the structure of nothing. This connection runs deeper still. The quantum fluctuations that seeded the cosmic web, in the first fraction of a second after the Big Bang, were rooted in the behavior of particles at the smallest scales, fields behaving in ways governed purely by quantum mechanics. The voids we see today are, in a very real sense, the amplified echoes of quantum events that happened before any atom existed. In a universe smaller than a grain of sand, those microscopic fluctuations, stretched and amplified across billions of years of cosmic expansion, became the filaments and voids we map today. The Boötes Void carries within it a memory of the quantum, a memory so old and so amplified that it now spans 330 million light-years of space. Small became large, quantum became cosmic. The void is the proof. It is worth pausing on that word. Proof. Science rarely uses it. Evidence, confirmation, support. These are the words scientists prefer. But in this case, the word feels appropriate. The existence of the cosmic web, the filaments and voids, the specific scale of the structures we observe, is consistent with the quantum origin story. A consistency verified by every new survey, every new simulation, every new measurement. The void is not just a curiosity. It is part of the evidence that the universe began the way we think it began, and that the quantum fluctuations of those first moments have left their signature everywhere, including in the largest empty structure we have found. The Boötes Void is, in this sense, a fossil. Not of any organism, but of the quantum state of the universe in the first fraction of a second after the Big Bang, stretched across 330 million light-years, still visible, still measurable, still teaching us about its origin. Inside the Boötes Void, there are 60 known galaxies. That number is worth dwelling on. In the observable universe, there are estimated to be 2 trillion galaxies. In a region the size of the Boötes Void, there should be roughly 2,000. There are 60, and those 60 are not spread through the void. They are gathered in a narrow filamentary structure through its middle, the remnant spine of whatever smaller structures merge to form the supervoid. What is it like to be a galaxy in the Boötes Void? We cannot know, in any direct sense. Galaxies do not have experiences, but we can describe the situation astronomically, and what emerges from that description is something that the word lonely is not entirely adequate for. A typical galaxy in a typical part of the universe sits within a few million light-years of other galaxies. Our own Milky Way is part of the local group, a collection of more than 50 galaxies, bound together by gravity. The nearest large galaxy, Andromeda, is 2.5 million light-years away. The nearest significant cluster, the Virgo cluster, is about 50 million light-years distant. We are embedded in structure. We are surrounded by neighbors. A galaxy in the Boötes Void is not embedded in structure. Its nearest galactic neighbor is tens of millions of light-years away. Beyond that neighbor, there is another gap. And beyond that, the edge of the void, where at last the cosmic web resumes and galaxies become more common again. But the edge of the void is hundreds of millions of light-years away. These galaxies exist in a kind of cosmic solitary confinement, isolated not by walls, but by the vastness of the emptiness around them. One of the 60 galaxies in the void has been given an informal name. It is sometimes called the loneliest galaxy in the universe. It sits near the center of the Boötes Void, with no close neighbors of any kind. It is a spiral galaxy, like our own Milky Way. It rotates. It forms stars. It presumably contains planets, some of which may support life. But the sky from a planet in that galaxy would be unlike any sky we know. The stars within the galaxy would be there, familiar and close. But beyond the galaxy's edge, in the direction where neighbors should be, there would be almost nothing. A handful of faint smudges, hundreds of millions of light years away, invisible without powerful telescopes. And beyond them, the edge of the void. And then at last, the filaments of the cosmic web, blazing with the light of thousands of galaxies. But even the nearest of those filaments would be hundreds of millions of light years away. In the night sky of any planet in the loneliest galaxy, the universe would look emptier than it looks from Earth by an enormous margin. There is a scientific postscript worth adding here. The 60 galaxies we know about in the Boötes Void are the galaxies we have been able to find so far. Detection is not perfect. Small, faint, dwarf galaxies may exist in the void without having been identified. Future surveys, with greater sensitivity and coverage, may raise the number. Some astronomers suspect there could be hundreds of very faint dwarf galaxies hidden within the void, too dim for current surveys to detect. But even if the true number is higher, the density of galaxies in the Boötes Void would still be dramatically below the cosmic average. Dwarf galaxies are far less massive than large spirals. Even hundreds of them, distributed through the volume of the void, would not significantly change the emptiness of the place. The Boötes Void would remain, in any meaningful sense, a great nothing. The 60 known galaxies are enough to establish that the void is not perfectly empty. They are not enough to make it anything other than the most dramatic example of emptiness in the observable universe. And yet those 60 galaxies exist. They form stars. They rotate. They evolve. They are doing everything galaxies do, in a setting of almost incomprehensible isolation. That combination, ordinary processes and extraordinary circumstances, is part of what makes the Boötes Void so compelling. It is not a different kind of universe inside the void. It is the same universe, obeying the same laws, producing the same structures, just with far more space between everything. The loneliest galaxy is still a galaxy. Its stars burn at the same temperature. Its gravity works the same way. Its planets, if they exist, orbit on the same schedule. The difference is only in the view. And the view, from inside the void, is almost nothing but darkness, stars within the galaxy. And then, in every direction, an emptiness that stretches and stretches and does not end for hundreds of millions of light years. That is the sky of the great nothing. The same physics. An entirely different universe. And perhaps that is the deepest thing the 60 galaxies of the Boötes Void tell us. The universe is the same everywhere. The laws of physics do not change. Gravity works identically in the void and in the densest cluster. Light travels at the same speed. Atoms form stars by the same processes. And yet the experience of being in the universe, the view, the context, the sense of what surrounds you, varies enormously depending on where you are. The 60 galaxies of the void are not lesser galaxies. They are not damaged or diminished by their isolation. They are fully functional, fully real, fully present in the universe. They are simply surrounded by nothing. And that nothing, as tonight has shown in many ways, is not trivial. It has a history. It has a cause. It has a future. It is, in its way, as rich with meaning as the most densely populated supercluster. The great nothing is only nothing if you are standing far enough away. Up close, it is everything. And it has always been everything, to the 60 galaxies that call it home. The Boötes Void raises a question that goes beyond astronomy. It raises a question about the limits of knowledge. Everything we know about the universe, we know because light has reached us from it. Light from distant stars, light from ancient galaxies, light from the cosmic microwave background, the faint glow of the Big Bang itself, still traveling toward us from every direction, having left its source nearly 14 billion years ago. Light is our only real window. We have other tools. We can detect gravitational waves. ripples in spacetime from colliding black holes and neutron stars. We can detect cosmic rays, high-energy particles that travel across vast distances and occasionally reach our detectors. We can detect neutrinos from the sun and from distant supernovae. But for the large-scale structure of the universe, for the maps of galaxies and voids and filaments, light is essentially everything. And light can only tell us about the things that emit it, or reflect it, or absorb and re-emit it. Dark matter does not emit light. Dark energy does not emit light. The vast empty spaces of the voids do not emit light. We infer their existence from the behavior of the things that do emit light. This means our map of the universe is a map of glowing things, interpreted to reveal the underlying structure. And the Boötes Void reminds us, dramatically, that the glowing things are not the whole story. The void is real. The emptiness is real, but we know it only because of the galaxies that are not there. What else might be in the void that we cannot detect? Not aliens in the science fiction sense, but real physical structures that do not interact with light in ways we can measure. Dense concentrations of dark matter, invisible to telescopes, primordial black holes formed in the first moments of the universe, too small and cold to emit detectable radiation. Structures made of exotic particles that we have not yet discovered, that do not couple to electromagnetism, and are therefore permanently dark to every instrument we can build. We do not know what is in the void, because we cannot see inside it in any complete sense. We know what is not there by the absence of galaxies. We know the void exists, and roughly where its boundaries are, from the distribution of galaxies around it. But the interior is, in a deep and not entirely metaphorical sense, unknown. This is not a reason for despair. It is a reason for humility, and humility in science is not weakness. It is the acknowledgement that the map is not the territory, and the visible is not the whole. The most interesting questions are often the ones we cannot yet answer. The Boötes Void is 330 million light-years across. We have found 60 galaxies in it. We know almost nothing about what fills the rest of its volume, and yet it is one of the best-studied voids in the universe, the most famous, the most analyzed, the most referenced in discussions of large-scale structure. If this is the most studied void, and we still know so little about its interior, then our knowledge of the universe is, to put it gently, an early draft. The universe is patient. The void has been there for billions of years. It will be there for billions more. And as our instruments improve, as our surveys deepen, as our models sharpen, we will fill in a little more of what we do not know. We will find more galaxies in the void. We will measure its dark matter profile more precisely. We will test our dark energy models against its growth rate. We will learn. But we will not learn everything. Not soon. Not easily. And that is fine. The universe does not owe us comprehension. It offers us questions and rewards the effort of asking them. The Boötes Void, in this sense, is one of the universe's most generous gifts. It is a place so extreme, so large, so empty, that it forces us to confront the limits of our knowledge directly. It cannot be explained away. It cannot be dismissed as a small anomaly. It sits there, 330 million light-years of nearly nothing, demanding that we either explain it or admit that we cannot. That demand is valuable. Science advances most quickly when it encounters something it cannot immediately explain. The void is still asking its question. Our models are still being refined against its existence, and future surveys will bring the answer, if not closer to certainty, then at least closer to clarity. The great nothing will continue teaching long after the last page of tonight's script has faded into sleep. That is not a small thing. Most of the universe's secrets require increasingly powerful instruments to approach. The faintest galaxies, the earliest light, the behavior of dark matter in the densest clusters. These require ever larger telescopes, ever more sensitive detectors, ever more sophisticated analysis. But the Boötes Void is already visible. It is already measurable. It is already one of the most studied features of the large-scale universe. The question it poses, why is it so empty? And is that emptiness fully explained by standard cosmology? Is a question that current and near-future surveys are actively investigating. We are not waiting for a breakthrough instrument. We are waiting for more data, more precision, more careful comparison between observation and model. That work is ongoing. The answer is approaching. And whatever the answer turns out to be, the void will have earned its place in the history of cosmology, whether it is simply an extreme but explicable feature of a standard universe, or a hint of something our models have not yet captured. It earned that place simply by being there, and by being, for so long, so much emptier than anything else we had ever found. That is a contribution. That is a gift. That is science, done by the universe itself, without any assistance from us. We live inside the cosmic web. That is a fact worth understanding slowly. The Milky Way sits in a region of the universe called the Virgo supercluster, sometimes also called Laniakea, a name from the Hawaiian language meaning immeasurable heaven. Laniakea is a gravitational structure, roughly 500 million light-years across, containing hundreds of thousands of galaxies. It is a large piece of the cosmic web, one node in a larger pattern of filaments and voids. Within Laniakea, the Milky Way is part of the local group, a modest collection of galaxies. The local group is not in a particularly dense region of the supercluster. We are not at the center of a rich cluster. We are not on a major filament. We are, by cosmic standards, in a fairly ordinary location. There is even a local void. Astronomers have identified a region of lower than average galaxy density around our position, called the KBC void, or the local hole. It is not as dramatic as the Boötes Void. It is smaller and shallower, but it suggests that even our seemingly ordinary position in the universe is not in the most densely populated part of the cosmic web. We are near the edge of a modest void within a supercluster, within a cosmic web that spans the observable universe. Understanding this location matters. It matters for cosmology because our local environment affects our measurements of the universe's expansion rate. If we are in a region of slightly below average density, then the universe may look like it is expanding slightly faster than it actually is, on average. The Hubble tension, a persistent disagreement between different methods of measuring the universe's expansion rate, may be partly related to our position in the local large-scale structure. Some cosmologists have proposed that our location in the KBC void contributes to this discrepancy. It matters for philosophy because it continues the long sequence of realizations that we are not at the center of anything. The Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of the universe. And the universe has no center, in the meaningful sense, because it is expanding in all directions equally. We are on the edge of a modest void, in an ordinary galaxy, in an ordinary supercluster, in a universe containing hundreds of billions of galaxies, organized in a web of filaments and emptiness, a web that stretches across 93 billion light-years of observable space. And somewhere in that universe, 330 million light-years across, the great nothing sits. A hole in the web so large that a civilization inside it would not know the web existed. We are lucky. Not in any cosmic sense, since the universe does not deal in luck, but in the statistical sense. Our location in the universe has given us a view rich enough to understand the structure. We can see the filaments. We can map the voids. We can trace the web. We can find the great nothing and wonder at it and try to understand it. If we were inside the void, we could not do any of that. We would be cosmologically blind. Instead, we are here, looking outward, at a universe full of structure, full of emptiness, full of questions that we are only beginning to learn how to ask. And from here, with the view we have, we can see the great nothing. We can measure it. We can wonder about it. We can trace its boundaries, count the few galaxies inside it, measure the dark matter deficit, and try to understand how something so large came to be so empty. We have been doing that work for more than 40 years, since Kirshner and his team first noticed the gap in their map. We are still doing it. The Euclid satellite, and the surveys that will follow it, will map more voids more precisely, and the Boötes Void will be part of that map, a landmark, a reference point. The great nothing, serving as a guide to understanding the smaller nothings and the nature of the forces that created them all. Our location in the cosmic web, seemingly ordinary, has given us the extraordinary gift of seeing it. The view from here includes the void, and the void, as we have seen tonight, contains more than it first appears. It contains science. It contains history. It contains questions. It contains, perhaps, civilizations that do not know we exist. And it contains, always, the invitation to look more carefully, think more slowly, and hold the unknown with a little more patience than it strictly deserves. We are also connected to the void in a way that is easy to miss. The same forces that emptied it, emptied us. The dark energy that drained the void of its galaxies is also pushing our own supercluster toward eventual dissolution. The cosmic web that surrounds the void, and in which we sit, is subject to the same long-term fate. Structure will slowly give way to expansion. The threads of the web will thin. The clusters will disperse. The universe will become more and more like the void, on larger and larger scales, as the eons pass. In the very long run, the Boötes Void is not an anomaly. It is a preview, a glimpse of what the entire universe will eventually resemble after dark energy has done its patient work across trillions of years. We are lucky to be here now, when the web still holds, when the void is still an exception and not the rule. And from this lucky vantage point, in this brief window of cosmic time, we can look outward and see it all. The filaments and the clusters, the voids and the nothing, the 60 lonely galaxies 700 million light-years away, carrying within their light a message that took longer to reach us than animals have existed on Earth. We can receive that message. We can read it. We can understand, at least in part, what it means. That is the privilege of our position. Not the center of the universe, not the most important location, just a place and a time with a good enough view to see what the universe is doing, and to be grateful for that view. Every void has a boundary, and the boundary of the Boötes Void is as interesting, in its own way, as the void itself. The Boötes Void is surrounded by some of the most richly populated structures in the observable universe. Its boundaries are defined, in part, by several enormous superclusters, dense concentrations of thousands of galaxies, whose presence marks the edge of the emptiness. Among these surrounding structures are the Hercules supercluster, the Corona Borealis supercluster, the Ursa Major supercluster, and the Boötes supercluster. These are vast agglomerations of galaxies, each one containing hundreds or thousands of individual galaxies, strung along filaments of dark matter that mark the edge of the void, like bright stitching on a dark fabric. The contrast at the boundary is striking. On one side of the boundary, galaxies are sparse, separated by tens of millions of light-years. On the other side, galaxies cluster together, gravitationally bound, interacting, some merging, some stripping gas from each other as they pass close by. The transition from void to filament happens over a distance that is vast by human standards, but compressed by the scale of the void itself. This boundary region is scientifically important for several reasons. First, it is where the effects of the void on surrounding matter are most visible. The low-density interior of the void pushes outward, slightly, through a process related to the expansion of the universe. Galaxies near the boundary, on the void side, are being very gently accelerated away from the void center, pushed toward the filaments. This effect is subtle and difficult to measure, but it is real. Second, the boundary is where the cosmic web becomes locally complex. The superclusters surrounding the Boötes Void are themselves connected to filaments extending in other directions, toward other voids, toward other clusters. The void is not isolated. It is embedded in the larger web, connected through its boundaries to the rest of the universe's structure. The Hercules Corona Borealis Great Wall, which lies in roughly the same region of the sky, is the largest known structure in the observable universe. It is a filamentary structure spanning approximately 10 billion light-years, which is about 10% of the diameter of the observable universe. The relationship between this enormous wall and the Boötes Void is part of a larger picture. A picture of large-scale structure in that region of the universe. The universe, at the largest scales, is a pattern of alternating emptiness and concentration. The voids in the walls are complementary structures. You cannot have one without the other. The matter that is absent from the void is present in the surrounding filaments and clusters. Conservation of matter ensures that every supervoid is balanced by extraordinary density somewhere nearby. The Boötes Void is balanced by the richness of its surroundings. The great nothing is bordered by great somethings, superclusters and walls and filaments that concentrate in a relatively small volume, the matter that has drained out of the void over billions of years. To understand the Boötes Void completely, you have to understand its neighbors. The void did not form in isolation. It formed as part of the cosmic web, shaped by the same gravitational forces that created the superclusters around it. The emptiness and the fullness are two aspects of the same structure, and standing at the boundary of the Boötes Void, looking inward and outward at the same time, you can feel the full weight of this. On one side, the richest structures in the observable universe, superclusters blazing with the light of thousands of galaxies, filaments running for hundreds of millions of light-years, nodes where clusters meet, and galaxies crowd together so tightly that they strip gas from each other as they pass. On the other side, the void, 70 galaxies where 2,000 should be. Distances between neighbors 10 times what they are in our own neighborhood. Silence measured in hundreds of millions of light-years. The boundary between these two things is not a wall. There is no sharp edge. Matter simply becomes rarer, more slowly, over distances that are themselves almost incomprehensible. But the contrast on either side of that gradual transition is as dramatic as any contrast the universe has to offer. Rich and empty. Full and nothing. The cosmic web and the great nothing, pressed against each other for billions of years, each one the consequence and the complement of the other. The boundary region of the Boötes Void is, in a sense, the most dramatic place in the observable universe. Not because anything violent happens there. Nothing violent happens there. No explosions, no collisions, no dramatic events. Just a very slow gradient, matter becoming less dense as you move from the surrounding superclusters into the void interior. But the contrast at either end of that gradient is overwhelming. You cross from one of the richest regions of the cosmic web to one of the emptiest regions of the universe. You cross from abundance to near absence, and the crossing, though gradual in astronomical terms, represents one of the sharpest transitions in the large-scale structure of the observable universe. To stand at that boundary, in imagination, and look both ways, is to hold the full range of the universe's architecture in a single view. Everything and nothing, separated by the long, slow, gravitational history of 13 billion years. The boundary of the Boötes Void is also a reminder of how every structure in the universe is defined by its relationship to what surrounds it. The void is a void because the superclusters around it are dense. The superclusters are dense because the void beside them is empty. Each defines the other. Neither could exist without the contrast. This is true at every scale in the universe. Stars are bright because space is dark. Galaxies are concentrated because the voids between them are sparse. The filaments of the cosmic web are visible because the voids give them contrast. The universe is a study in difference. In the space between things, in the meaning that emerges from contrast, the Boötes Void and its rich surroundings are the most dramatic example of that contrast we have found. And in that drama, there is a kind of beauty that no other structure in the observable universe quite matches. We have come a long way tonight. We began with the shape of the universe, the cosmic web of filaments and voids that emerged from the quantum fluctuations of the Big Bang, amplified over billions of years by gravity and dark energy, into the intricate foam-like structure we see today. We followed a team of astronomers building a map of the sky and finding in their data a region where the map was simply blank, 330 million light-years of space, containing a fraction of the galaxies it should. The discovery that launched decades of investigation and one informal but unforgettable name: the Great Nothing. We explored what the void contains. The 60 known galaxies, gathered in a thin filament through its center. The dark matter that remains, far below average density. The intergalactic gas, too thin and too cold to be called anything but nearly absent. The vast interior, most of which has yielded nothing to our telescopes. We sat with the thought experiment. The Milky Way inside the void. A civilization of scientists looking out at a universe that appeared to be only one galaxy in an infinite emptiness. The conclusion they would have reached, confidently and wrongly, that they were alone. The entire cosmological enterprise they would have built on a foundation of invisible incompleteness. We thought about dark energy and the void as a laboratory for its measurement, about neutrinos and the way the size distribution of voids encodes information about the lightest particles we know, about what future surveys will teach us as they map more voids more precisely and test our models against the most extreme emptiness the universe has produced. We thought about the 60 lonely galaxies and what it might mean to exist in isolation that profound. And we thought about the limits of knowledge, the humility that comes from recognizing that our map of the universe is built from light, and that what does not emit light is not included in our map, however real it may be. And now we are at the end. What does the Boötes Void teach us? It teaches us that emptiness is not nothing. It is a structure. It is a record. It is a consequence of the same physics that created every galaxy, every star, every planet, every person. The void and the filament are made by the same forces, shaped by the same history, part of the same unfolding of the universe, from its first moment to this one. It teaches us that where we are determines what we can know, not in a limiting way, not as a complaint, but as a fact about the physical universe. Knowledge is perspectival. Our cosmology is the cosmology of beings in a specific location, with a specific view. Different locations would have produced different cosmologies. The one we have is extraordinarily lucky. We can see enough to understand the shape of things. We should not take that for granted. It teaches us that the universe is mostly empty, not mostly full. The bright threads of the cosmic web are the exception. The dark spaces between them are the rule. The Great Nothing is not an anomaly in a universe full of matter. It is the dominant character of a universe in which matter is the anomaly, concentrated in thin bright threads across an ocean of void. And it teaches us that the scales of the universe are genuinely beyond ordinary comprehension, not beyond mathematical description, not beyond scientific investigation, but beyond the intuitive grasp that we use for ordinary life. 330 million light-years is not a number that means anything to the part of the brain that evolved to navigate a forest or a savanna. It requires a different kind of understanding, a slower, quieter kind. The kind that comes from sitting with a number for a long time, letting its implications unfold gradually, not trying to feel it all at once. That is what tonight has been for. The Great Nothing is 330 million light-years across. It has 60 known galaxies in it. It has been growing slowly larger since before the Earth existed. It is teaching us about dark energy and neutrinos and the structure of everything. It contains, perhaps, civilizations that believe they are alone in the universe. And it is a reminder, the most dramatic one the universe has yet offered, that what we can see and what is true are not always the same thing. The void does not care whether we understand it. It simply exists as it has existed, vast and cold and mostly empty, asking nothing, offering everything, to anyone patient enough to look. And that patience is what tonight asks of you, not to grasp the 330 million light-years all at once, not to feel the full weight of the emptiness in a single breath, but to let it arrive in pieces. A number here, an image there, a thought that settles slowly, the way dust settles in a room, coming to rest on every surface without noise. The universe is not in a hurry. It has been expanding for nearly 14 billion years, and it will continue expanding long after every star has burned out. The Boötes Void has been growing, almost imperceptibly, for most of that time, adding a few light-years to its diameter every million years, as matter very slowly migrates toward the surrounding filaments. By the time our sun reaches the end of its life, the void will be slightly larger than it is tonight. By the time the last stars in the universe fade, it will be larger still. And after the stars are gone and the galaxies have dispersed, the universe will have expanded so far that no two galaxies can see each other. The void will simply become part of the general emptiness, indistinguishable from everything around it. But right now, tonight, it is still there. Distinct, measurable, extraordinary. 330 million light-years of nearly nothing, surrounded by the bright web of everything. And we are going there together. Now let all of that become soft. Let the 330 million light-years fold in on themselves until the distance becomes a feeling rather than a number, a sense of scale, a kind of quiet. Let the 60 lonely galaxies drift further away, each one still burning, each one still turning, each one surrounded by a darkness deeper than anything in our experience. Let the cosmic web settle around you, with its bright threads and its vast empty spaces, its ancient structure and its patient unfolding. Let the void be the void, and let yourself rest somewhere inside the small bright thread of the universe where you happen to be, surrounded by 100,000 million stars, in a galaxy that is, by any cosmic standard, extraordinarily close to its neighbors. You are not in the great nothing. You are here, small and present and real, in a universe that is paying no attention to you, and is, for that very reason, entirely yours to wonder at. Good night. If this journey left something in you, please consider liking or subscribing. It helps other curious minds find their way here. Good night.